You guys can come back here. We'll start the lab. No, I'm going to hand out a lab today. I'm going to do a quick demonstration, and then we'll give you a piece of paper and let you guys work on that activity.
Individual effort, or?
Oh, you can have a partner.
All right.
Let's come over here really quick, and I'm going to show you some quick slides on ESD. So you guys can come over here, and then when we start filming, I'll have you stand where you are. That's a good spot. But for right now, let's come over and look at these slides. So, you know, we talked a lot about static electricity, and today we're talking a little bit about ESD safety as well. So I got these slides here. These slides, this is from a company that makes the charge coupled devices, the ones, you know, like you touch the screen, capacitive touch sense devices. But you can see what they're showing here. It says static is not always fun. They're showing pictures of metal traces that have been blown up from static electricity, because those aluminum traces are very small. And you know, we talked about today when when you rub, it's mechanical friction is transferring electrons from one to the other that can build up, and when you discharge that, then that constitutes an instantaneous pulse of current. It's just for an instant, but that instant of current can be 100 amps for just an instant. Okay, and that's enough to cause a wire to fuse. If we're talking about 10 microns or 5 microns wire on a semiconductor level. If you could grab one of those big semiconductor packages right back there for me. It's right there on the table. Right there. No, right over there. Yeah. Yeah. So yeah, you can see this package here. Now inside of this package, this is plastic, of course, then you have pins on it. So when a lot of times when this runs down in a production environment, a lot of times they'll have these slide down, you know, for manufacturing and things like that. Right. So that charging effect can charge the device, and so if you come over here and then go to touch it, it could shock. You could transfer it through a pin, and then that would destroy the device. Yeah, that's usually the way it works. And electrostatic discharge is the number one failure in any manufacturing type of environment. It costs the companies the most money, so there's very strict ESD procedures on what they require you to do. We'll go through the video some more of this. So up to 500 volts, the human body can charge to hundreds or thousands of volts. Now many times when you discharge yourself through a knob, you can't even tell that it's there, but a device could tell it. Right. You're only going to feel like around thousands range, but it can damage the device even just 20 volts or something. Once discharged from the fingertip to a CCD is possible, creating an electrostatic event. Tiny spark requires about 500 volts. Just to create a small little spark, 500 volts. So that's pretty significant. And a lot of these devices are designed for 1.8 volts, 3.3. You know, so we're talking about pretty significant results. Of course, we already talked about triboelectric effect. It's the friction and the rubbing, the mechanical transfer of electrons from one surface to another. It says it's not the rubbing, which was alluded to as well in the book. If you read it, they alluded to the fact that it may not actually be the friction; it may be just be simply the contact. And that's one thing they found too, is that it only really takes contact with a dissimilar material to actually cause that transfer of charge to occur. Rubbing just increases the contact, is what it says. When we rub two different materials together, which become positively charged and the other one negative, and then we have the series that we talked about. When two materials are rubbed together, the one higher on the list gives up the electrons. And humidity that has been found to discharge the electricity that comes on a component package. But it says you cannot rely on humidity. So you can see here that it says if the humidity is high, the moisture coats the surface of the material, provides a low resistance path for electron flow. And then this path allows the charge to recombine, thus neutralize the charge. If it's very dry, then it's going to be more sensitive. And it says typical voltages walking across the carpet, 35,000. Relative humidity, 35,000 volts at 10 to 20% relative humidity. Walking over vinyl floor, 12,000. Worker at bench, 6,000. So these are the voltages you can generate. Common poly bag picked up from the bench, 20,000 volts. So it's very significant. Very significant damage that could occur. It says, as the table shows, the travel electric charging persists even at high relative humidity. Humidity does not eliminate the need for conventional safeguards. And then they have a chart for field-induced charge. Now, remember, you can also charge something with not even touching, just by being close to it, you can charge it as well. Like today, when I was getting my finger close to the ball and it was moving around,
Right.
that shows that you can affect things at a distance.
Right.
And then this shows again some more. The CCD is one of the most ESD-sensitive electronic components manufactured. Without ESD protection diodes, most scientific CCDs are susceptible to discharge even at 50 volts. It says this ESD event can cause bus lines to melt. It has a picture here of it. What happens is a lot of times when a part fails in the field, they'll take it and they'll put some material to eat the plastic away, and they'll actually take a picture of the part and do failure analysis on it. And they'll try to figure out what caused it, and 95% of the time it's ESD.
Oh, okay.
Yeah, so. Although any semiconductor device can be damaged by spark, moss, metal oxide, semiconductor devices are particularly susceptible. So one point I want to get across today is what devices are really exceptionally sensitive to ESD, and that is metal oxide semiconductor, MOSFETs, which is anything digital. It's going to have MOSFET devices inside of it. We have some MOSFET transistors over there. The bipolar transistors, not as much. The diode, not as much. Not very much at all, really, to be honest. But the digital devices, the digital ICs, even some of the analog ones, you have to be careful with because they have MOSFETs inside of them. Yeah.
So how many of the ones that we have here do you think are destroyed?
80%. 80% of them
are already destroyed?
are destroyed. Oh no, they're not already destroyed. The reason they're not destroyed is because they put ESD protection diode clamps inside of here. Okay, so as a designer, when you're IC designer, you have to go evaluate each pin, figure out what type of pin it is, and then you choose an ESD structure for it, and then you put it next to the pin, and that pin is tested at typically 2,000 volts human body model, so they'll actually zap it at 2,000 volts, and 500 volts for charge device model. So they got different models. Basically, the way they view your body is a capacitor. 2,000 a capacitor charges 2,000 volts through a 1K resistor. That's the model that you are as a human. You're like a capacitor that's charged to 2,000 volts with 1K series resistance. That's how you're viewed from an ESD standpoint. And so when you touch this, it's going to charge through you to the part.
So the little modules they put in there protect against the spike?
Yeah. So these chips have probably all been weakened by ESD, but the only reason they still survive in your phone and everything is because precautions have been made. Now, that doesn't mean that's only 2,000 volts. Now, and that's only assuming one shock. So it's perfectly, this chip could be blown, it could be damaged, it could be weakened. It's not always a catastrophic fault. Sometimes it's a degradation in performance. They've actually shown that you can take an analog op amp, for example, move around, shock it. It'll still work, but with reduced performance.
So it create higher resistance in the circuit.
Yeah, like the output impedance would be increased, the input impedance would be increased,
Okay.
reliability, long-term reliability would be reduced. Yeah.
The mechanism that you're saying that's used in there to protect the device, it's kind of like a surge protector? Is it
Yeah.
designed kind of like a surge
Surge
protector?
protectors use Zener diodes a lot.
Right.
Yeah, it's a diode clamp.
Okay.
Yeah, we'll talk about diodes later. We haven't talked about that
Diode
yet.
clamp is what it is?
Uh-huh.
Okay.
Well, the most basic structure is a diode clamp.
Okay.
Yeah, it clamps the voltage so that it won't exceed a certain voltage. And the reason that the MOS devices are so sensitive is because it has a very, very high input impedance. And so when you have a current flowing through a high resistor, Ohm's law says you're going to have a high voltage. So then that can blow through the gate oxide, because the gate oxide is clear glass. So you basically have a clear piece of glass, and then you have metal on both sides of it, and it can actually break through the glass and cause that to short at very high voltages. So it's kind of like lightning or a spark. It breaks through. Like electricity is not supposed to flow through the air, but sometimes it'll break through if it's high enough because of the charge. And we talked about that. There's layout precautions in here. Here's an ESD protective device you can see on the screen here, 2 diodes, back-to-back diodes. Here's how they view your body as 20,000 volts into a resistor, and then that's the device right there. And these are just some backup slides. Here's a continuous monitoring type typical setup. Is you'll have a floor mat, conductive floor mat, and then you'll have ground mats over here on the table. You'll have a wrist strap. What the wrist strap does is it grounds yourself. Now, can someone grab, actually, could you grab a wrist strap over there? I forgot to grab the wrist strap. And Rod, do you mind grabbing that ESD bag too? I forgot to get my ESD stuff. The conductive bag on top of those books, those brown books there. Sorry about that. I got it. This is why I'm always running around like a chicken with my head cut off. I'm trying to get everything ready. Sometimes I forget. So you got the wrist strap that you put on you. Okay. I'll try to get this on there. It's kind of hard to put on by yourself. And then inside of this you have a 1 mega ohm resistor to prevent, it's a current limiting resistor. You don't want the current to go too fast. And then this side would be grounded. You could put it to the safety ground here. I mean, I don't really recommend that, but that's basically what it does. They have these things that you plug in here, actually. So you have the mat.
Right.
See, and they have these little devices you plug in here. They're over there right now. I have to move this stuff around because we used to have that protected, but now we're going to have this protected. I just haven't gotten around to doing it.
Those are all grounded.
And this will plug into here. This mat is conductive, and then those things you plug this into are grounded through safety ground. So effectively, it's the same as plugging in there, even though it kind of looks bad to do that. Now, you're grounded. Any sort of charge that is on you as you're moving around or whatever is going to be dissipated into the ground.
Right.
So everything's going to be good. Now, some facilities allow you not to wear this, and then what you do is you have heel straps. And what it does is you put it around your shoe, and it's a device like this, similar to that, conductive, but it goes inside your sock, or actually goes under your sock where it's wet.
Right.
It's kind of moist under there, so it creates a good connection. And then they have conductive flooring. So then you can walk around and always be grounded.
Right.
Assuming you're not running.
If I'm wearing my boots, I wouldn't be grounded. Electrical boots I have at the house that are insulated.
Yeah.
Goes around the outside.
Oh, it
Yeah.
bypasses them.
Well, nothing's a perfect conductor, nothing's a perfect insulator.
Right.
But that will create a pretty good conduction to ground to protect the devices. And the typical procedure, for example, let me just get right here really quick so the camera can see it, but the typical procedure, if I had this component laying here on the bench, and if I wanted to move this component over to another workstation to work on it, the procedure would be is that you put on your wrist strap, okay? Well, okay. Can someone help me? Okay. Put on your wrist strap. Actually, you can leave this on once you get it on. And then you would test it with a monitor system. You test it to make sure it works, and it's just going to, you touch a panel on the wall and just make sure that you connect to the ground. And then you put this on, you connect this to your ground system. Then you pick up the part. If you want to transfer it, then you can put this in conductive foam. If you want it to be better, like this pin's bent right here, so this one's already been damaged. So you couldn't even sell this shit probably. And plus, we touched it the wrong way, so we definitely could not sell that shit.
Right.
Put it in the bag. Now you can take off your strap. Now you can walk around. Now, if I'm walking around here, am I generating electricity?
Sure.
What's happening? If this is a conductive bag, is the electricity going to touch the part? Why is it going to be safe in here?
Because
Electricity's all over this.
It acts like a Faraday cage.
What does that mean? Faraday cage.
The electricity goes around the outside of the bag.
Only on the outside. Why?
Right.
Why is it only on the outside?
Path of least resistance. Does that have anything to do with it?
What type of charge do you think is positive or minus that's on right now? It doesn't. I mean, you don't know.
Right.
Yeah.
But it's going to be one or the other.
Right.
Let's say it's positive. Is it going to be attracted to each other, or is it going to be repelled from each other? It's all going to be repelled. So it's all going to be squeezing on the outside edges of the bag, right? So it's never going to go on the inside of the bag. That's right. It is a Faraday cage, but you have to know what that means. That means that the electricity is always on the outside and never goes on the inside. So you're generating electricity. Now you move it to your next workstation. You put it down. You put on your wrist strap. Okay. You sit down. You make sure you have a mat down that's grounded. Oh, sorry. That was just a disaster. Make sure that your mat's grounded. And put it down here. Keep your wrist strap on. Then you can go ahead and start soldering on or whatever you need to do to it. So that's the typical procedure. Any questions on that? Yeah.
We're going to be graded on the procedural steps?
Yep. Certainly. All right. Now,
And what does you said it needs to be wrapped in a conductive foam?
you can put this in a conductive foam, and that's better for it because it makes sure that all these are the same levels. Because if this pin is a different level than that, then
Right.
they could, it could
Right.
cause current to flow.
Will it be in a conductive foam in the bag? Or will it be
Yeah.
in either or?
In manufacturing facilities, they got all kinds of ESD stuff. They got those tubes you put this in that's conductive.
Right.
Everything in ESD environment is conductive. So plastic is not plastic in an ESD environment.
Right.
Plastic is a special conductive plastic.
Right.
Okay.
Yes, sir.
And you're not allowed to have papers at your bench. Why not? You can't have papers if you're over here,
It's no swing.
Right.
or rubbing it against this or rubbing whatever. Because why? It can generate
Right.
electricity.
Right.
It's not allowed to have any papers
Yes, sir.
in your area.
So.
Or drinks or whatever. Foam is really good for generating electricity.
Right.
Like today, we had a foam plate. We just rubbed it. Really, really good to generate electricity.
What I'm asking is, whenever we're tested on this, will you be giving us? Will we be tested with the bag, or would it be just whatever specs to the company that we're?
I'll just
doing?
ask the question: how do you properly transfer a component from one place to another?
Okay.
Put it on a wrist strap. Put the part in an ESD safe bag.
Okay.
Carry the bag to the new place. Put on your wrist strap again.
Okay. Okay.
Or make sure you have conductive feet straps.
Right.
Should you have any papers at your workstation? No.
Yes. Okay.
Should you have drinks or
Gotcha.
any styrofoam at your workstation? No. Things like that.
Okay. I didn't know whether you'd be asking if we'd have to do it in a show procedure, like showing you what we need to do.
Yeah.
In this environment, do we use the bags, or is that basically how you?
In this environment, we will practice, and I'm going to get these mats set up so that we have ESD so we can practice it.
Right.
But here, if it happens, it's just like, okay, you throw it away and you get a new one, which we don't really want to do that. When you have more expensive parts, you want to be more careful.
Absolutely.
If I had a $20 microprocessor over here, you definitely want to make sure that or sometimes in the computer upgrade repair class, we had $20, $30 penny processors.
Yes.
We're taking out of the bag or memory, and I was very strict with that because I don't want to go buy another processor or another memory because those are expensive. So really, that's the main thing. If you got a really expensive semiconductor device, I would make sure that you handle it properly.
Right. Okay.
Okay, let's see. So today we're going to do this. We have this lab here. And before we do this lab, I'd like to just show really quickly how to use the instruments that we're going to use today. Now, I'm going to be trying to film this one. So this power supply here, it's got some buttons that you have on it, okay? Now, the normal mode for this power supply is all the buttons will be out, okay? In the non-depressed position, okay? Now, in that position, you have three knobs over here, and you have a voltage knob, you have a fine voltage knob. The fine voltage just increases it slowly. You have a current knob, and you have two sides. This is a double supply, so you have one here, and then you have one in the middle, This one in the middle, it goes from 4 to 6.5, and it's just a small little supply. It doesn't have all the features that the ones on the side do. The reason we have the dual is because we can set this supply up for. Can you just make sure that? Make sure this gets on film. So the dual supply here is set up where you can have a positive and minus supply. For example, let's say that we had a case where we needed +5, -5 voltage, okay? And then we had a ground in the middle. So the way we would set that up is we have the plus minus, a plus minus. So what we do is we connect this plus to this minus, okay?
Rigid.
We put those in series with each other. Now what that means is this is now the reference point. We're going to define this as being the reference point. Ground. Now if I'm referenced to this ground and I connect this voltage here, then I'm going to have +5 here. And if I set this supply to 5, then this is going to be -5 volts relative to this ground in the middle. That's not fitting in there very good. The supply is not very good. Actually, give me another one of these. Can you guys give me one more of those? This one may be damaged. No? It's the power supply. Yeah, so this one may not be a very good power supply to use. Now, what's going to happen if I make this the ground reference?
You have 10 volts.
Then I have 10 volts here. What if I make this the ground reference? There are negative grounding systems, right? What if I make this plus the ground? I say this is ground, and I'm going to connect this to. I connect this to the chassis of my car, and say, okay, this is going to be ground, and then this, what is that?
-10.
-10. Okay. Now, let's say that I want to. Okay, let's say I want to current limit this. Now, what's going to happen if this is a current limiting supply. Now, a battery, you couldn't do this to, but with a current limiting supply, I can connect those together. That's created a short circuit. Okay? But this light came on. This red light says CC, current control. It's controlled by current right now. Now, I can't see the current. Well, if I push this button, notice that this button right here, it says V and A. So if you press it, it's going to show you the amperage.
Okay.
Now, as I start to turn up, now it's current limit. Now as I turn up the current, it's going to increase the current. Okay? So if I want to current limit this supply to 1 amp, that's how I would set it. Now when I let go of it, the current goes down to 0. Okay? If I put a resistor in here, a variable resistor, then as I change that variable resistor, this would go up and down. The current would go up and down. But the voltage should stay the same as long as that red light's not on. If that red light turns on, the way it's going to limit the current is it reduces the voltage. Okay?
So when you connect that voltage should drop.
What? Yeah, the voltage will drop. And you'll see a little spark there too as well. If you turn this up high enough, you can see a spark. If you turn the voltage up high enough. So that's how you basically limit the supply. What else can we do here? What other cool features does this thing have? We have serial mode. Look, notice that we have a parallel and serial. If we push serial, then it's going to put the supply in series.
Right.
Now, if I connect this, let's put this on there, and we'll put that on voltage. Oh, actually, series is right. Series is up.
Out.
Yeah.
Right.
Now these two are in series, and notice that. Okay. Notice that over here I have voltage. Over here I have current. Okay. I can change the current. I can reduce the current. Over here I can increase that. I can turn this current knob all the way up, and I can increase the current over here, Okay? Now if I let go of this, you can see the current goes down to 0. Over here I have 5 volts. But now you're also going to have a voltage on this side too. It's actually going to be about 10 volts because they're in series now. Does everyone see that?
About 10. So you add the 2. And
Yeah.
Okay.
If you're in series mode, then you're going to add the 2.
Right.
Now when you're in parallel mode, if I push this button, what that does is it puts these 2 supplies in parallel
Right.
internally. Now what does that do?
Gives you more current.
It gives you more current. Yeah, what that does is it gives you more current. So let's try this out. Let's see. Yeah. So now this side over here, this one's in parallel, and so when you connect these in parallel, you'll be able to get double the amount of voltage of current out of it. But I don't have the connectors, but you can connect those in parallel and you get twice the amount of current out of it. Now this knob here gives you the ability. Notice here you have 0 to 30, and then you have 4 to 6.5. So the 4 to 6.5 over here. Let's measure this really quick. The one in the middle. We talked about the ones on the side, which really gets us into talking about this Fluke digital multimeter. We call it a DMM. Okay. Okay, let's connect this. 5.5. Notice that you can change that. This says 3.9. I can turn this knob all the way up to about 5-6 volts. Okay. And so this one you can use for like a basic digital. Sometimes people use this for digital. If you have some digital circuitry here, maybe over here you have plus or minus 15. So you can have plus or minus analog voltage, and you have a 5-volt digital. So that's really what that's for. In the early days of digital, most everything was about 5 volts. These days it's more like 1.8, really low voltages. It's not as useful today. Now let's say that I'm going to do a quick little circuit here, just a quick measurement with the digital multimeter. Okay, let's put this on 5 volts. All right. It's on 5 volts.
So it's put in there a resistor. Light bulb.
Let's put everything out, so in the out position, okay? Now let's just put this, we'll put it all the way down. Okay. And we'll just put the current to a safe level. When you very first start to do a project, I would say turn the current down, just to be safe, turn the voltage down. And then what you can do is see, I turn up the voltage a little bit and the light comes on. So there, now we got the light burning. So turn up the voltage. See there? This is actually a 5-volt light. If you turn it over more than 5, then it's probably going to blow out. If you push this button here, you can see that it's about 70 milliamps.
0.07.
Yeah. If you want to put it through this side, if you want to see current and voltage at the same time, you can turn that voltage down and turn the current up. And then you have to put these together. The same thing because you turn this voltage down. So this is 0, but you have 5 over here, and now you can view the current on this side. So now you have both a voltage and a current meter, so you can look at the voltage and current at the same time. Okay, so that's what we're going to do today, basically in the lab. I want to see if you guys can set that up. What else I want you to see that you can do is, can I have someone get me 2 more of these? A black one and a red one. A lot of times what I'll do on this DMM is I will replace the meter. You don't have to, but okay. I'm going to replace these with clips because it makes it a lot easier sometimes. Now what I can do is just I'm going to put these in series. Now when you, oh, I'm sorry. Yeah, let's put this on amps. Now when you put it in, when you want to measure current with these, what you have to do is you have to move the lead over. Okay, you have the common, the black goes to common, the red has to move to the amp setting, and you have to turn the meter to amps. Okay, now this thing is set up to read current. Now for current, I talked about it being a through variable. You have to force the current to flow through in a circular loop. Now it may be hard to see that right here, but what we have is the current is going to flow through the black lead, through the common, out the A. Now that's just so the polarity will be right. You always want the current coming out of this side of it. And the current's going to go into the common and then out of the A amp. And then here's my LED. Now, so the current is going to be flowing out of this amp meter because it's going to have to go through the power supply, through the amp meter, and it's going to go through the light bulb. Okay. Now let's turn it up. But the problem is this amp meter may be blown up because a lot of times what happens is the fuse is blown up. Now the fuse that's going to be blown up, this is what happens. If you try to measure current and you stick it right across here in parallel, it's going to blow the fuse up. So can somebody give me another, maybe give me that one over there? We'll try another one.
Is it only a 10 amp fuse that's in there?
Yeah, it says 10 amp. See, there you go. So please don't blow up my fuse. I beg you. So I'm going to have to go figure out and go replace that fuse. But now you can see that 62 milliamp. And you can see this is a little bit more accurate than that. This only shows the 10th milliamp place. Any questions? Everybody good with that? Let me just read this really quick and make sure that you guys should be good. Okay. Okay, also, can you grab me just a capacitor from over there and a diode if you can find one? Yeah. The other features of this DMM is, I didn't tell you about voltage, but voltage should be pretty intuitive, right? You simply put the voltage across what it is you want to measure. Okay? So if I want to measure the voltage across the lamp, I put this across the lamp. If I want to measure the voltage across this, and I simply put it across it. And you have to make sure, of course, that this is on voltage, because a lot of times you forget that it's on there, just like I just did. So measure voltage. The other features of this DMM is you have resistance. Okay? And if Rocky could grab me just a resistor really quick, but first I'll do this capacitor. You see this reading here that says shows a little capacitor symbol? Mm-hmm. Right there, does everybody see that? The yellow capacitor symbol. It has two lines, and it says yellow. Okay, that's for capacitor. Now, all you got to do is put on capacitor and then hit the yellow button. That'll switch it to that mode, and then you can measure your capacitor. And it tells you the value of the capacitor. Also, it has a diode mode. Okay, the diode is the little symbol with the arrow with the slash line through it. That's the diode symbol. You guys know all about it. Right there, that's a diode symbol. Yes, right there. There's an arrow with the line. Okay, diode. I'm going to give everyone a diode. And what you do is you have to have the diode. I don't have one, but I'll give you one here in a minute. But the diode, you simply just put the diode, if you've got one.
Will it test the LED as a diode?
Yeah, it'll test the LED too. On diodes, you have a polarity.
Yeah.
Now you have to make sure that the slashed line, that looks like a negative sign, goes on the negative lead. And if you do, it'll tell you what type of a diode you have, if it's working or not. And also tells you the voltage drop across that diode. Oh, here's one. So the slashed line here, see the white line on there? That's indicating negative, the white line. So the camera, white line on this side. So you put the meter with the black side on the negative line, the slash line, and then it'll measure, say this is 0.97, 0.497. So the bigger the diode, the lower that number is going to be. Like if it's a small diode, it'll be about 0.7. So the larger, the less drop you have. And you can measure LEDs and things like that. Sometimes these things may be bad. So if you're troubleshooting, sometimes you need to measure. When you measure these, make sure it's not electrified. Okay? If it's electrified, it's going to screw up the reading. It's not going to give you a correct reading. Same with resistance. If you go to measure on this meter the ohm symbol, the ohm symbol is the Greek omega character. Okay, ohms, everyone knows what ohms, that's the ohm symbol. If you put it on ohms, it's going to measure resistance. The higher the number, the better the insulator. Okay? Now, when you measure resistance, it cannot be electrified. Okay, if it's electrified with voltage and current or whatever, it's not going to give the correct reading, and it may mess up your meter. Hopefully, it won't, but it could mess it up. Now, one of the number one things we use, and we do this a lot, is you'll hear the beeping sound. Now, to get the beeping sound, it's called continuity testing, and it has the four arc type symbols on it. Okay? Now, I'll just put it further. That's the continuity testing. Now, when you connect those together, that's going to tell you whether you have a connection or not. Now, this is useful when you're prototyping a board. Then you have your components in here, and you say, "Well, I don't have, nothing's working." One thing you can de-electrify your board. You can go and you can check to make sure that this component lead is connected to this component because you know that it should be. So you can verify that those two ends are connected together by using the continuity feature on the device. For example, let's show you how to do this. Now, if you look on the back of this, you'll see those metal bars on the back of it? Note the direction that the metal bars are facing. Okay? Okay, so those metal bars mean that these connections will be made when you put something in there. So if I connect, let's say I connect this red wire and this yellow wire in that same horizontal bar, and I look on the back of it, see that's the connection. But it will not be connected if I move it down. So that's connected. I know this is the basics for some people. Okay, that's connected. Now if I move it down here, okay, that's not connected. Those two wires are not connected. Okay? Sorry if some of this is too elementary for some people, but so this is not connected. Across this bridge is not connected, but the red lines and the blue lines in the middle, the red line is all connected and the blue line is all connected. So if you put anything through that line, we typically use the red and the blue. The red means positive and the blue means minus. So what I want you guys to do is connect your lamp and your, let's see, I don't know if you just follow the instructions. It's going to want you to set up a lamp where you have a continuous path of current, and measure, set up your power supply, set up your ohm meter, and then you're going to measure a few components. And any questions before we get started? Or you can ask questions in the lab. I'll walk around and make sure you guys pass a couple of those out. Pass a couple of those out. This helps me get feedback on what you guys have learned, and if you got that? Okay, you got that one.
Any table?
What's that?
Any table?
Yeah, just grab any bench that has a good working equipment.
Yeah.
And
Not gonna use the O-scope there?
no, I'm not going to use that.
Okay.
Yep. The light bulbs are right here. I'll put them over here on the table.
Momentarily.
And you can bend the leads apart so that they won't short. That's what I would suggest, since we got a lot of them. And you got your wires over here. You can work on teams of 2 if you want to work on teams of 2. If you want to work by yourself, then that's fine.
Mr. Halstead,
Some people work better on their own.
Can I use your flute, Mr. Halstead? Can I use your flute?
Yeah. I wouldn't use power supply because it's got a bag.
Right, we're going over there. Thank you, Mr. Halstead.
Yeah, there's one on that bench in the corner there.
Oh, really? And this thing has a bad. I've come across that several times. Yeah. Is that? Oh, that is mine. No drinks allowed.
I saw that there.
No drinks allowed. Oh, except for me. I'll try to go through fast. I want them.
Awesome. There you go. There you go.
Okay, so we have that. I think I'm just going to turn this thing off now. Check this out over here.